so grateful you joined me tonight in your journey of learning chemistry. In this video, I want to introduce, it's at a fairly basic level, our model for understanding metallic bonding. Now, metal structure can get complicated. It depends on, there's interfaces between metal layers and defects, and we're not going to get into that at all. We're going to talk about the very basics of this. So, metallic bonding involves a positive metal ion, hence metallic, right? A positive metal ion surrounded by valence electrons. I like to consider this like it's like a commune. So, for example, the aluminum ion, the aluminum would become 3+. Its 3 valence electrons play all over the place. So they play at each other's house. They move freely from home to home. Okay, so I call it like a commune. They can play at anybody's house. They have dinner at anybody's house, spend the night, hang out, and they're free to move. Metals are typically described by what is often called a free electron model, or more simply, a sea of electrons. And that's because these electrons can move throughout the structure like a sea can freely flow. Okay, electrons that are not fixed in a bonding structure are called delocalized. That's a very important vocab word. They are not fixed to a particular location. They're delocalized and can move. Okay, now when we make this or the structure as at a first level understanding, the metal ions are arranged in a fixed lattice. So you've got kind of a lattice structure if you went through the positive charges there, much like a lattice fence. And then the valence electrons freely move. They kind of play, is what I like to say in loose words. They freely move throughout the lattice structure. Now, I just want to point out these are not discrete molecules. A metal doesn't have a fixed beginning and end. It depends on where you cut it. So I want to just like to emphasize that it's not like a discrete molecule like water is or ammonia. Those are discrete molecules with a very fixed beginning and end. These are more like ionic. They go on and on and on until somebody breaks them or cuts them. Now, metallic bonds have very high melting points because they're strong bonds. So it takes a lot of energy to break. If it takes a lot of energy to break a metallic bond, that's going to give it a high melting point and boiling point. And they're really kind of all over the place. There's not any pretty trends that we can follow. There's a couple of groups that follow a trend, but a lot of the groups will go up and then down. So it's not something that I would typically have my kids memorize trends of, but just to be able to explain that it takes a lot of energy to break the metallic bond, which is what happens in a phase change, is you're actually breaking a metallic bond, and so it's going to have a high melting point. They'll conduct electricity in their solid because electrons are freely moving. I have freedom of motion, mobility of my electrons, I have conductivity. When you melt it, again, electrons are free to move, conduct electricity. They tend to conduct heat very well. Get a metal cup if you've gone camping and you have those metal camping cups. My coffee just does not stay warm in those because it conducts heat away from my coffee so quickly. And again, that's because you've got a lot of kinetic energy involved and motion with that sea of electrons. Metals have a luster due to light reflection. They are malleable. They can be hammered into a sheet, and they're ductile. Now, it's positive, 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 right? It's alternating positives, but those positives are buffered from repulsion by the movement of those electrons throughout the structure. So I can add a stress, a force on a layer, and the positives still don't repel the positives because you have this like buffering region of electrons that prevent them from experiencing excessive repulsion. And that's why they're malleable and ductile. So, thanks for joining me. Good luck with chemistry.